Saxon Advanced Mathematics, Lesson 15. Take a deep breath, you guys. Get a drink of water, stretch out your back, grab a sandwich. This is a fairly long lesson, and the topic is proofs. And these are proofs that I definitely want us to work. They are manageable, they are not difficult, they illustrate some really fun things about proofs, and we're going to enjoy this. The first thing that we need to have are some postulates. Postulates are assumptions that are agreed upon by mathematicians to be true. There's another word that means pretty much the same thing as postulates. Axioms are things that are agreed upon to be true by mathematicians. The word postulate, this word is used by all branches of math. And postulates is a word that is specific to geometry. So they mean pretty much the same thing. Postulates and axioms. It's an assumption that is true. And this is a word that all mathematicians use, and this is what the geometry freaks use. Okay, so the first postulates of geometry, which is kind of redundant, were coined by a dude named Euclid. He was, he was Egyptian, probably. He probably lived in Egypt, and we're talking about 300 BC. And he was in Egypt, as best we know. So that was a long time ago, you guys. He was thinking about this stuff and writing down these 10 postulates that we still use in our proofs to this day. So they had sticking power. So here are the postulates. 1, 2 points determine a straight line. Let me just show you something. They're written down very nicely in your book, right here on page 115, okay? So if you want to see the full wording of them as they're accepted now, this is where you can go. I'm just going to draw pictures and chat about them because I don't want you to be overwhelmed. And you know how I feel. Words don't really capture mathematical ideas as well as numbers, letters, and shapes do. So let's not confuse ourselves. So 2 points determine a straight line. A straight line extends infinitely in either direction. We know that. That's why we put the arrowheads on them. A circle may be drawn with any given center and any given radius. Now, I drew the circle first, but what they're saying is pick a point, determine a radius, and now you can draw a circle. That one was not a very good circle, but you get the idea, right? A circle may be drawn with any given center and any given radius. So pick the center, pick the radius, and now you can draw a circle. That one's better. Okay? 4, all right angles are equal. Well, that makes sense, right? A right angle is a right angle because they're all 90 degrees. So all right angles are equal. This one is a little bit longer, but it's not more difficult. Given a line N and a point P, there exists on the plane of P and N, so in other words, we're not going three-dimensional here. Let's just stay on a piece of paper. There exists on the plane of P and N and through P, one and only one line which does not meet the given line N. What they're saying is if you have a line and a point, you can draw a parallel line, but there's only one. Does that make sense? A line and a point, you can draw another line that is parallel to the original line. 6 is one of my favorite. Things that are equal to the same thing are equal to each other. So if A equals B and B equals C, then we can say that A equals C, right? Equal things are equal to each other. 7, if equals be added to equals, the sums are the same. right? So if we say that A equals B, then we can say A plus, okay, let's just say this. If A equals B, then A plus D equals B plus D. That's an algebra rule, right? You can add the same thing to both sides. 8, if equals be subtracted from equals. So same idea, except this time we're going to subtract D. Okay, that's also a rule of algebra. 9, figures which can be made to coincide are equal. So in other words, if we have a segment that is 5, and then we draw another segment that is 5, you can take that and visually flip that and make them coincide. And they work. And then the last one, 10, the whole is greater than any part. And I can't think of a good way to illustrate that. The whole is greater than any part. We'll wait and see if we come up with a, I mean, that intuitively makes sense to me. I don't argue with that. But I can't think of a good example of how to show that. So we'll come back to that. So these 10 postulates are tools that we can use when we're trying to prove things, right? When we work on our proofs, we can use these to justify certain assumptions that we're making as we work through the proofs. So these postulates are our tools, and we will use them, you'll see, in these new proofs that we're doing. Flipping. That sunshine just wants to get me today. And I know it wreaks havoc on the train. No, it just doesn't want to. It's too sunny. Oh wait, I think I know what I can do. Stay right there. Let's see if this works. I hung a dish towel on the back of the chair that my camera sits on, which is helping. The only problem is that I have to stand here and hold it. No, you know what I can do? I'll use one of my other textbooks as an anchor. Wow, you guys, COVID has driven me to some pretty crazy places, but none crazier than this. Okay. Look, it's better. I think that's better. Okay. Technical difficulties, right? Here, let me adjust it down here. Oh, it's nice. It's like a little light box. Okay, that's better. All right, example 15.1. We're going to actually start working some proofs here. All right, now there are a lot of words involved in this, and I'm going to try to cut through the words and focus on the pictures and keep it simple. All right, we start, it says, this is what John tells us. The median of a triangle is a segment that connects a vertex with the midpoint of the side opposite the vertex. So he's defining for us what a median is. And we'll come back to that in a second, because right now it's just a bunch of jumbly words. Prove that the median drawn from the vertex formed by the equal sides of an isosceles triangle bisects the angle at this vertex. All right, let me help you break that down. We're drawing an isosceles triangle. Isosceles means two sides match and the third one doesn't. There's our isosceles triangle. The median drawn from the vertex formed by the equal sides. Okay, these are the equal sides. So we've got a median drawn from the vertex formed by the equal side. So that's this vertex. Bisects the angle. All right, the first sentence told us that when you draw a median, it connects with the midpoint of the angle opposite. Okay, so we're drawing the median. Now, because we drew it as a median, we can say, oh, look, these two sides are the same too. And what John wants us to prove, let me get a different color. But I have to get a good different color. Here, this will work. Okay, John wants us to prove that these two angles are equal. Or, as we say, congruent. Because what we're trying to say, we want to say that these two angles, this line bisects the angle. So these two have to be equal in order for that to be true. They're bisected. That means cut in equal parts. Okay, so we know that, oh, let me put letters on here so we can. Okay, so this is the way John wants us to organize our thoughts in these. We're going to a table. We're still not being super particular about this, how we present this information. I mostly just want you to understand it. How you write it is of secondary importance to me. Understanding it is huge. Okay, so we call these, this side is the statement, and this side is the reason. Okay? So the first thing we're going to say is that segment AB is congruent with segment CB, okay? This is the same as this. We can say that's true because that's the definition of isosceles. John writes it out longer. I don't want to spend a lot of time writing out a bunch of gibberishy words. I want you to understand it. We put these tick marks here because we drew an isosceles triangle. That's what John told us to do. Second statement. I need to add another letter. BD is median of side AC, okay? BD is the median of AC, and again, that was given to us. We were told to draw this line as the median, and we were told that a median hits the midpoint of the opposite side. So we just did what we were told there. Third thing, AD is congruent to CD, okay, because of the definition of a median. We were told, again, in that big sentence I read here, I'll read it again. A median of a triangle is a segment that connects a vertex to the midpoint of the side opposite the vertex. So we were told that's the definition of a median, and we were told to draw the median. So we know that these two have to be the same because this is the midpoint. Okay, 4. This is my favorite. Remember, this is the symbol for congruent. It's like equals, but it's for geometric shapes instead of just numbers and letters. So we use it just as if it were equal to. All right, and what we're saying here, again, the circle is the shape that we use to say this. This line is a side of this triangle and of this triangle. And we know it's the same because it's the same line, obviously, right? So we can say it's congruent, right? But we use a circle when we are trying to say, hey, look, this line is actually a side of two different triangles. Now we've done something fun, haven't we? We have got side, 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 side. So we have proved that triangle, let's see, what order should we say it in? ABD is congruent to triangle CBD And the reason, oh, just a second, I need to go back and do that one. The reason we say these are the same is by side, 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 right? That's our congruency postulate that we're using here. I skipped over the reason that we can say BD is the same as BD. That's called the reflexive axiom. Notice it's axiom rather than postulate. So we're using rationale from a broader part of mathematics. Things that are the same, right? So that's the reason we use when we're saying something so obvious that it's the same. We call it the reflexive axiom. I always think of it as take a look at yourself in the mirror and you see yourself, right? So that's what this is. Okay, so now we have proved that these two triangles are congruent by side, side, side. And now we can say that angle ABD is congruent to angle CBD because corresponding parts of congruent triangles are congruent. Makes sense? This is the most confusing part, I think, because we're stating things that are so obvious that it's hard to even state them. But what this proof boiled down to, like all proofs, is we turn things into triangles. These already were, but we create triangles and then we prove that the triangles are congruent using the congruency postulates. And then we can get into the specifics of whatever we were trying to do. The next example is a really great example of how we look for ways to make triangles. Example 15.2. Prove that if two tangents to a circle intersect at a point outside the circle, then the lengths of the tangent segments are equal. Okay, let's draw a picture. Here's a point, here's a point. Here's a point outside the circle. I'm going to draw a line from this point to that point, and it will be a tangent, right? It's not perfect because I'm a human being, but it's the right idea. Okay? So we're trying to prove that the lengths of the tangent segments are equal. So we're trying to prove this. Blue is what we're trying to prove. And I'll write it in blue. Prove that tangent segments are equal. Equal or congruent, same length, however you want to think of that. Okay, so what we want to do in this, the trick to proofs, is try to find a way to turn things into triangles. So I want to turn these two segments into triangles. And here's the way we're going to do it. We're going to put the center of the triangle in, and then we're going to create two triangles by connecting the tangent points to the center and then connecting the center of the circle to the point outside. What we have done is created now two triangles, and we can say some things about these triangles. Let's make our chart. I usually make the reason side a little bigger, and honestly, life is short, so I just write S for statement, R for reason, okay? So let's start organizing our thoughts. We need some letters so we can talk about this. This is P, and these lines continue on. They don't have to stop at P. This is A. This is B. The center of the circle is often referred to as O, which I don't quite understand, but all right. So AP and BP are tangents to circle O. And that was given. We were told to make it that way. 2. We can create the radii, the radiuses is radii with 2 i's, which is fun. Okay, we added these 2 radii, and we added this line. The reason we can do that is because of one of Euclid's postulate. 2 points determine a unique straight line. That's the first postulate. So I'm just going to write 2 points give us a line, all right? That's how we can justify adding those lines. 3. We're going to talk about these segments a little bit, and this is something new. Segment OA hits segment AP at a perpendicular, so we can add a right angle box there. And the reason that's true is that tangents and radii I'm going to write this in layman's terms. Tangents hit radii at a right angle. That was part of the definition way back when we first started talking about tangents, is that they create a right angle with a tangent. So that's just a fact of tangents that we can refer to. And then we have one here as well, OB and BP. Okay, so we added those to our diagram. So now we know that this seems like overkill to me, but this is how John lays it out. That means the angle OAP and angle OBP are right angles. And we can say that because perpendicular lines create right angles. See how we just have to go in baby steps and just explain everything out like it's like no one understands anything just because it's perpendicular. Now we have to say, well, perpendicular lines make right angles. That's the part of proofs that annoys me. They're fussy and extremely particular. It's more important to me that you see, oh yeah, okay, this hits there, it's perpendicular, that means it's a right angle. Those thoughts are all connected, and here we're having to break them into separate thoughts. That's fussy. 5, I'm gonna run out of space. So that means that triangle OAP and triangle OBP are right triangles. And that's the definition of a right triangle. Right? A right triangle has a right angle. Okay, again, we stated the obvious. All 3 of these represent one single idea in my head and possibly in yours too. So that's silly. Okay, so what we can do though, what we can see much more directly is we're in a hypotenuse leg situation, aren't we? Because we've got right triangles. We know that these are the same because they're the same line. This is reflexive axiom, right? This line is in this triangle, this line is in that triangle. And then we've got these two lines that we know have to be the same because they're both radii, right? They both represent the radius from O to the edge of the circle. So look what we've got. We've got hypotenuse, leg. So we can say that the triangles are congruent. Triangle OAP and triangle OBP are congruent. Oh, I can say it like that. I don't need to write the word out. I can use the symbol. They're congruent, and we can say that is by hypotenuse leg. And then we can say that this side must be the same as that side by corresponding parts of congruent triangles are congruent, right? Because they're the matching, they're the reflections of each other. So I don't have room for that. I'm just going to squeeze it in. I'm just going to say segment AP is congruent to segment BP. Okay? If you're finding this part to be the confusing part, then take a deep breath and blow it off, because that's not important. What's more important is you can see, how did we construct triangles out of what originally didn't have triangles, and then how do we use those triangles to find one of the congruency postulates? And here we determined they were right angles, and then we could do hypotenuse leg. This is the hypotenuse, these are the legs, and then that proves that those sides must be equal to congruent. Okay, I don't want to focus on this, and I feel like I'm saying too much about that. I think this next one, I won't write it down at all. I'll just talk you through the picture. Example 15.3. That's what I'm going to do for the rest of these, you guys. I'm not going to work on the statement and reason part. I just want you to understand what we're accomplishing. All right, prove that the sum of the measures of the angles of a triangle is 180. Okay, well, we've talked about that for a long time, haven't we? That the sum of the interior measures of a triangle are always 180. So let's see if we can prove it. There's a fun way to do it. A, B, C. Okay. Again, if we can create more triangles, more angles, that usually helps us prove it. This one has a fun one. We're going to take this point. We've got this line here and a point up here, and we're going to create a second line that is parallel to the first line. And there's a postulate about that, isn't there? That for any line and point, you can draw a second line that goes through the point and is parallel to the first one. So I added those two signs. Now we know that they're parallel. And I'm going to number these angles 1, 2, and 3. Now, if we use our imaginations, we can extend this line and see that we've basically created transversals here, right? And then we can extend this one out if we want. That's a transversal. And we can extend this one out. Does that make sense? I haven't drawn any new lines. I'm just extending the, well, I drew this one, but other than that, I'm just extending the lines that we have. Now we can see that using this line as our transversal, this angle here is the same. You know how they do large, small, large, small? So this angle, 3, oh, it's off this one. That's what was confusing me. Look at this line. It cuts through here. And so this is also angle 3. And this is also angle 3. Make sense? And before I get into all that, let me just say, obviously, angle 1 plus angle 2 plus angle 3 all add up to 180 because they are a straight line, right? So we drew this line, and we can do that because of one of Euclid's postulates, Euclid postulate. We can say that these 3 angles add up to 180 because that's the definition of a straight line. We can say that this angle, this is the one I want, is the same as angle C. Okay, this angle is angle C, according to my original picture. And we can see that that is the same as 3 because these are small angles on this transversal. And then let me just put this in a different color to help your eyes see it. Let me change the color of this one. And then this angle 1 is going to be the same as this, right? So we can say that angle A equals angle 1. Let me try doing this one in a different color too. I think that helps make it pop. Three is there, right? And then 3 is here. It's the same angle. So we can say that this angle C is the same as number 3, and this angle 1 is the same as angle A, and B is the same as 2. Okay, so we have used transversals to find the corresponding angles, and then we're matching the numbers up with the letters. Now we can take this, and this we all got by the definition of transversals, right? And this is the definition of a straight line. Okay, now we can substitute in, instead of this, we can say, instead of angle 1, we're saying angle A. Instead of angle 2, we're saying angle B. And instead of angle 3, we're saying angle C. These should all have those on them. And we said that 1, 2, 3 equals 180. Then we said that 1, 2, 3 equals ABC. And so now we can say that ABC equals 180. And that is, this is just by, let me see which reason John gives. Substitution. Okay? That's how our thought processes worked. We drew the parallel line, then we extended these lines to say that lines go in an infinite direction. We created 1, 2, 3. We can say that those are definitely adding up to 180 because they're supplemental. They form a straight line. Then we use transversals to match the angles to other angles. And then we showed that angle A of the triangle is the same as angle 1. Angle B of the triangle is the same as angle 3. No, I'm sorry, this is C and 3, B and 2. And then we just substituted the letters into the numbers and proved it. If you want to see more of how John wrote it out, it's here. Again, my focus is on helping you build the understanding of how we go step by step. We still have more to do. Stay with me. I think this is, you guys, our meatiest. We have some more proof lessons, but this is the toughest one. It's the longest, and it's the mind-bendier one. Use the 6th and 8th postulates of Euclid to prove that vertical angles are equal in measure. Okay, and the picture we draw ourselves is some vertical angles, and we just letter them, A, B, C, and D. So we want to prove that these are vertical angles. And the thinking on this is fairly straightforward. And John tells us to use the 6th and the 8th. So let's look and see what they are. The 6th one is things equal to the same thing are equal to each other. And the 8th is if equals are subtracted from equals, the remainders are equals. Okay, so we're trying to prove that vertical angles are the same. So we can say that angle A and angle C are vertical. And that's by definition. Or you could say it's given, because John told us to draw vertical angles. Now, what we can see is that A and B add up to 180. And B and C add up to 180. Okay? And these are both because they form a straight line. Right? A plus B, B plus C. So we can say that A plus B equals B plus C because things equal to the same thing are equal to each other, right? They're both equal to 180. That should be plus. They're both equal to 180, so we can say they're equal to each other. Now we can subtract. So this is the sixth postulate. And now we can subtract B from both sides, and that's the eighth postulate that says if you subtract the same thing from equals, then the result is equal. And so when we subtract, we get A equals C. And that is exactly what we were trying to prove. I didn't write that in the beginning. It said prove that vertical angles are equal in measure. So we were trying to prove that. Again, I don't care as much about the presentation. John's is way neater and nicer. You can look at it here anytime you like. What I mostly want you to get from this is that lovely little aha moment when you go, oh, yeah, that's 180, that's 180. Subtract the B out of both of them, and they're equal to each other. And properly, we should put it like that. And our final one would be, oh, that's just fine, how it is, all right? So that is our fourth one. We have two more. This one is presented more like what we saw in our first system of truths. It says, it's got a figure for us. Let me draw the figure. Given BD is the, oh, I need the letters so you can see. BD is the angle bisector of angle B. So we're told that these two angles are the same. It's the angle bisector. And we also know then that these two must be the same because an angle that, median that bisects, if it bisects the angle, it will also bisect and create a midpoint. And so we know that AB, we're also given that AB is congruent to CB. So we're given that these two are the same. Oh, John doesn't want us to assume this. He wants us to prove that. All right. Prove that AD is congruent to CD. Okay. So we know that these two are congruent because we're given that. We know that this is the angle bisector, so then we know that those two are the same. And we know that BD equals BD, so we know that this side, this triangle and this triangle each have a shared side, so that has to be the same. So that tells us that these two triangles are congruent by side, angle, side, and corresponding parts of congruent triangles are congruent. CPCTC. All right, so all we really had to do was mark down what was given to us, and then notice this, and then that gets us to, so we use the reflexive axiom to say that BD equals BD. And then we used side angle side to prove congruency. And then we use CPCTC to prove that those two must be the same. Okay? Again, John writes it out with more flourish and style. But it's important to understand his thinking process before you try to make sense of his notes. Last one. We have a shape, and as I'm drawing it, I notice it's got arrowheads on it. And I go, oh, that means these two lines are parallel, and I immediately start thinking about transversals. Maybe we'll need them, maybe we won't, but I'm thinking about them. Okay, Q, LMNOP, Q, R, S. And then there's also a diagonal drawn through this. Okay. Given angle Q is congruent to angle S. All right, so this one and this one are the same. And segment PQ is parallel to SR. Okay, we know that because these little lines are in there. So we added those. Write a 2-column proof to prove triangle, so prove triangle PQR is congruent to triangle RSP. Okay, so we won't have to do any corresponding parts business because we just are trying to prove the whole triangles are congruent. So we just have to get ourselves to one of our congruency postulates. Side, angle, side, 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 angle, 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 side, or hypotenuse leg, right? We're just trying to get to one of those because all we need to do is prove the entire triangle is congruent. So let's see what we can do. We know that these angles are the same. And we know that this side is the same, right? That's reflexive. So we've got that. Now, let's just try this. What happens if we extend these lines out so it looks a little bit more like a transversal? And let's just extend this one out because that's the one that chops through it. Okay, well now let me turn it a little bit so those lines are straighter for me. Right? That's the way I'm used to looking at them. My book and my chair legs. Okay, that's a little bit weird, but that's the way we're used to looking at transversals, right? With the parallel lines like this and the angle cutting through. If we could prove that some of these angles were the same, that would help us a lot, wouldn't it? Well, this one and that one should be the same, shouldn't they? Because there's the transversal and there's the parallel lines. And these are both, if you look at that's the larger angle, that's the larger angle. This is the smaller angle in the same transversal. So I think we can say those match. Okay, let me move my book back now. And let's see what we've got. We've got one matching angle, two matching angles, and one matching side. So we've got angle, angle, side, and we know that if we've got that, then we actually have all three, because if you can prove two angles, you know the third one has to match because they have to add up to 180. So there is how we prove congruency, by using the transversal. And the way I knew to use the transversal is that once it was established that those lines were parallel, then I thought, ooh, parallel lines, that's transversal country. And I spread them out. Here is John's formal thinking on that. He got to the same conclusion as us, right? He did the reflexive axiom. He did, here's the transversal. Here's how he figured out the angles were transversal. He used the transversal to figure out that those angles were the same. He stated something obvious. He used reflexive axiom, and then he got to angle, angle, angle side. So our thinking was the same as his thinking. He presented it in a more formal style. That I know you can copy. What I want you to do, you guys, when you approach these problems in the homework, and I don't think there are tons of them. There's a few. Let me just show you. Here's one. Okay, you'll do 5. You won't do 6. What I want you to do is draw the diagram, put the information on it, you know, with the markings, the way that we do, and see if you can figure out how you would prove that those two triangles are congruent, all right? So it's gonna be one of your postulates, one of your congruency postulates. Think it through and see what you could do, how you would go about proving that. Then once you get the idea in your head, just jot down a few notes, add to the picture, and then just say, side angle side or whatever you think is gonna be the solution. Then go look at the way John presented the answer. And in the beginning, I just want you to copy down his format, listing all of his formal steps so that you understand the way he slowly builds up the evidence in order to come to his conclusions. What's more important to me is that you draw the proper conclusion, and then you can use his answer as an example to build the detail. But I definitely want you to think through the proof and come up with your own strategy for solving it before you look at the solution. If you are having problems finding the strategy, coming up with the right congruency postulate, tell me, I want to help you with that. If you can figure out the right congruency postulate and you're just stumbling over the details of how to write it down, that's fine. That's not something that you learn that falls into place quickly. You'll learn by using John's example. What is important is that you write down your guesses at how you would solve this before you look at John's solution. That's really important to me. So I will be talking to you about proofs in our video calls for the next couple weeks. I want to make sure these are not suffocating you. But again, keep them in perspective. It's not something we're going to build on. This lesson is really the most intense that we're going to get. Okay. Whew, that was a workout. We're done. Lesson 16, we just go back to some nice clean algebra. So we can look forward to that. Okay, thank you. Bye.